residues values of this green cycle, while these values of VCB determine the normalized covert triangle. The second reason is that this FCNC induced semileptonic decays, for instance, B2K style plus L minus, are sensitive to the new physics because they are forbidden tree level. The third reason is because we can compute this semileptonic decays in theoretically, and these semileptonic decays are clean, at least compared to hadronic decays, and the theoretical uncertainties is under control. And in this talk, I will only cover this exclusive decays. I will emphasize this inclusive decays. So the first example is exclusive B2 pi LU decays, and which is relevant to the extraction of VUB exclusively. Actually, this is the best way to extract VUB from these inclusive channels. I will basically explain the calculations of this form factor B2 pi for the non-consumer's approach. The basic idea is the correlation functions in QCD is due to the sum of these hadronic states. For B2 pi form factor, we will start with these correlation functions from vacuum to pi, and we interpolate this B method with the local current, and the first one is the transition current. And for this small transverse momentum, where this pi moves very fast, almost on a light cone, we can compute these correlation functions using light cone ODE. It has a general form as of the convolution integral of this Hall-Scattering kernel with increasing twist and this pi distribution amplitude. This can be also understood from the following diagram. The first one is the Lee diagrams, the second one is the higher static contributions, the third one is the QCD corrections. And of course, we can also write down the hadronic dispersion relations for these correlation functions, and then we just match these two different representations, and we will get these final samples where we already place this hadronic spectrum density by this QCD spectrum density, which is the so-called semi-local duality, because we only need the integral to be equal. Now in this slide, I will show you how the shape of the form factors in the small Q-square region will be influenced by these input parameters. The first one is this uncertainty induced by this Geiger-Moore moments of twist-to pi distribution amplitude. You see, it is the uncertainty become visible only for Q-square is larger and close larger than this 8GV square. The second one shows this uncertainty from this normalization, so this twist-to distribution amplitude, that means this current parameter mu pi, which is actually a constant, which is independent of Q-square, because mu pi is just a constant. And the third figure shows the uncertainty is due to this normalization scale. It is clear that this scale environment, these fluctuations of the environment scale become much more important for the increase of this transverse momentum. And the last one is due to the variations of the internal parameters of Samuel's approach, namely this Borel mass and this threshold parameters. And since the Samuel's is only valid for small Q-square region in order to show that we have like OPE, so in order to extend the form factor to the large Q-square regions, we need to parameterize the form factor in a certain way. A less model dependent way is the so-called this Z parameterization. Basic idea is that we perform the conformal mappings of the form factor from Q-square plane to these Z planes. And here we basically follow this BZL parameterization. We don't include this additional out functions here, which will change this Q-square behavior near this threshold. And we also try truncated expansion to the second order. Just a quick remark is that such kind of deparameterization actually will not work near this B star threshold because it changes too quickly and the parameter Z here actually close to 1. This is different from B to D form factor. And this next update of B to pi form factor is done in 2011, and this solid code corresponding calculations of some rules and extended to high crystal regions with these parameterizations, and this ray means correspond to the lattice HP QCD predictions, and this balloon triangle correspond to the graphs of this milk and formula graphs, and they are in general agreement for this high crystal region, even if we just initialize this form factor graphs from no Q square to large Q square. Okay, now you may wonder what this plot will just show this comparisons between theory and experiment. We consider this normalized Q square distribution, which is independent on VUP actually. So again, this solid code corresponds to some root calculations, and this Ray square corresponds to the Baba analysis. The first pair of Baba, there are two pairs actually. The second pair is the ratio of the second pair is showing these balloon triangles, and it is claimed that the second Baba pair up is more advanced because they include more data sets, and also they include their techniques of reconstructions of the domains and the resolutions of the structurals and so on. And the magenta for cycles are from below, and in general you can say that the shapes are in reasonable agreement, but the only problem is that you may wonder if this small Q square regions whether the shape is positive or negative from this external side is not so clear now. Okay, now we can extract UV purely from the sum calculations of the form factors. We focus on the following normalized decay rate, which is again independent of UV because we have tracked it. In the massless lepton limit, of course, only this vector form factor S plus will enter into this quantity, and then we just employ our predictions of form factor. We also analyze these uncertainties from the variations of different parameters. It's clear that, as explained before, the most important parameters are actually the scatter moments and these color parameters in reality of triangle scale. This is this internal parameters of samples is Boron mass and the threshold of lacking samples, and also the Boron mass and the threshold parameter of these 2-point QCD samples for B mass and constant. And then if you match this samples calculation for this delta zeta and this bar measurement of two sample in the battery, you will get the following answer. The central value is 3.5 with uncertainties, so roughly speaking 10% level. However, if you just compare this exclusive VUV with inclusive VUV quoted by in this PDGQ sample curve, which is actually 4.4 with more or less 3% or 4% uncertainties, you may find that although they are more or less in agreement with 2 sigma level, however, if you just research on the central values, actually they are quite different. This is a long-standing this VUV part, which we still is not clear. And now comes to the second part of this talk. It is radial decay of B2K style as MI. As mentioned before, this decay couldn't happen in tree level because they are induced either by these penguin diagrams and also or these box diagrams. So actually we expected that they could be relevant for this searching for these new physics. And these decays are actually very important, has very rich phenomenology from this experiment side, and here I show some recent measurement from this LHC from the theoretical side, we couldn't provide too much information here. And this plot shows isosphene asymmetry of BGK plus remarkably, this isosphene asymmetry is very large in the small Q square and also suffer from these large uncertainties. The last plot shows this 4 macrosymmetries of BGK star plus I minus. This is also the first measurement of this zero cross point for macrosymmetry for BGK star plus I minus. It is 4.9 plus minus 0.9 CD squared. Now we may wonder how we explore this rare case from the theoretical side. The leading contribution actually from 3 operators is electromagnetic operators O7 and 2 semileptonic operators. So this contribution from these 3 operators can be decomposed into the hadronic part and the leptonic tensor. It is clear that the hadronic part is just the form factors. So then you may wonder there is nothing new compared to BQ pi because we only need the only dynamic quantity is still this form factors. Actually, this is not true because these effective operators will be multiplied with the Weyerhaeuser coefficient, which is dependent on the geometry scale and the scale. So it means that this matrix element will be multiplied by this scale dependent Weyerhaeuser coefficient, which means that the decay amplitude actually depends on the geometry scale, which is in the life factorization. So you may wonder what happened here. How do we solve these problems? This comes to the story of the hadronic operators. The hadronic operators come to the game when they combine with QD interactions. So the quarks, there are 3 types of these operators. First line I show is current operator, which can be generated in G level. And the second line shows this QCD Part I. The last one is this current magnetic operators. It is worthwhile to mention that this QD correction to the matrix element of the hadronic operators will not be reduced to the form factors. So this means that this non-dependent dynamics of this FCAC case is actually much more involved compared to standard semileptonic case. The reasons are as follows. First is there are the so-called Hall-Stock interactions which will not generate these local operators, at least at this W mass scale. Within this factorization theory, we can still find that we can after integrating these hard or hard-collinear modes, you still can get some local or light operators. The secondary is that the soft glow radiation certainly don't generate these soft local operators, which I will explain in much detail in this talk. Probably the simplest argument is that this matrix element actually involves strong phase, which never happens for this form factor. So the strong phase is actually also Q-squared. Now let's come to this various contributions of hadronic operators. The first type of this contribution are induced by these corrections to these 4-part and magnet operators. This square box shows this weak vertex and cross with cycle show the photon radiations. And this is the leading order diagrams, which is well known since the 1980s. And these 2 diagrams are just the polyphasic corrections to these leading order diagrams. Actually, this type of diagrams actually are very important because they will generate these large logs like log Q square over MB square, in particular for BK star plus M minus. The last one is generated by this color magnet operator O8, the gluons attached to this, to the bottom part of all these, and also the symmetric diagrams. The photon can be different in any place. For these 4 type of diagrams, we still can, this amplitude of these diagrams can be still written as these form factors because this spectral quark actually definitely participate in the interactions. However, the situation will be changed when if you consider these hard-stack interactions. There is a gluon attaches this quark group and this spectral quark, and the photon can be emitted everywhere. This external rays and this internal quark group. This is the spectral interaction generated by this moment. And these two kind of contributions actually will compute in the framework of QCD factorization in 2001. And the third type of contribution is of annihilation topology. This is a leading order diagrams with photon radiated from these four quark fields, and the leading contribution is obviously from this photon radiation from this light quark inside the beam mason. And it has been shown that this weak annihilation contribution is actually factorizable if this transverse momentum, which is also this lepton pair in mass, is larger than hard collinear squares. Otherwise, you will get these endpoint singularities. It is also clear that these diagrams will also generate strong waves in time-like Q squared. However, these polyvariant corrections to weak annihilation topology has been computed. That is actually the reason why there is still some remaining scale dependence in the final amplitude, which is proportional to alpha s multiplied with Penguin operator Wechsler coefficient. Actually, this is even probably important for this isospin symmetry relation, which I will explain below. The last type of diagram are the so-called soft gluon radiations. Soft gluon can be emitted from these quark loops and also generated by this color bucket operator of H. So the simplest way to estimate these two types of contributions, of course, there's power quantities. Using this SCT power quantity, you can clearly find out that these soft gluon radiations are power space. So you may wonder, why are we interested in such kind of these power corrections? The answers are as follows. First, the leading order factorizable quark group without any gluon emission is actually expressed by the color factor. The second and more important reason is that for B2K star L plus L minus, this non-factorizable quark group will be enhanced by MB squared over Q squared. So this is a very huge factor when Q squared is small, around below 6 GeV squared. Okay, I will basically explain how to compute soft gluon radiation from this Chung-Yuan group. This matrix element is defined by this time-ordered product of the electromagnetic current of Chung quark and these three operators. And when the transverse momentum is small, you can certainly apply this Latican OP for this time-ordered product of these Chung quark fields. Diagrammatically, you have the following diagrams. The first one is this leading order diagrams with these three Chung operators. There is no gluon radiations. In the second diagram, there is one soft gluon radiation from this quark loop and these two soft gluon radiations. Since there is no additional enhancement for these two gluon radiation diagrams, so I will jump out such kind of contribution and only focus on these one gluon radiations. And performing this Latican view will get out this following non-local effective operator, which is slightly separated actually. This omega is this spectral quark momentum inside the B mesons, and the combined derivative will act on this dual gluon field strain tensor, and now you can have opportunity to understand why this local OP actually doesn't work, because you simply expand this function in the local limit, you will get a tower of these operators with increasing dimensions. If you focus on the numerator in the square brackets, this correct derivative acting on this gluon field strain, so we pick up this soft momentum K and the scalar product, which is actually of order MB times standard QCD. And it's clear explanations of this local expansion has been discussed in the context of the inclusive B decays to XS gamma in 1997. Now I will explain how to compute this matrix element. We still follow the standard philosophy of radical ensembles, but now we put the B method on the left here and interpolate decay by local current. This is just the effect operator we obtained before, and then we just write down these quadratic distribution relations for this correlation function and isolate the ground state contributions, and then we match these quadratic representations to the QCD calculation errors, and in QCD this nonpolynomial dynamics of correlation function will be characterized by this three-part capital B method. Now let's come to the numeric, so this soft global effect, and for the phenomenological equivalence, we normally absorb this Chung effect into this Wesson coefficient of C lines, which is one of these dominant semileptonic operators. The first one is from the factorizable part group, the second one is from non-factorizable part group. And this dashed curve corresponds to the contribution from non-factorizable Chung means the soft global radiation from this Chung group. This dot dashed curve corresponds to factorizable Chung group. It's clear that these two contributions are actively co-influenced, and remarkably this non-factorizable Chung group is 30% correction to this factorizable Chung group. Similarly, you can follow the similar, you can work out this Chung effect for B2K star plus M minus. Only this dynamic structure is a bit involved, and then different from B2K star plus M minus, actually there is this enhancement of this soft Chung contribution in the endpoint regions due to this real photon as mentioned before. Numerically, this Chung effect will bring about 20% corrections to C9. Now let's come to this Chung effect for these physical observables. The first one is this differential branch ratio for B2KLL. It is clear that at small q square, this effect is not visible. Only when you try to approach this Chung-Li ratio, then with this step size, the role of this non-factorizable Chung actually becomes more and more important. The second plot shows for like a symmetry in B2K star plus A minus. This dashed curve corresponds to contributions without any Chung effect, and the solid curve includes all of these soft contributions and factorizable contributions, and you can see here this Chung effect will shift this zero cross point to the left hand approximately 10%. Since we have both these hard collinear and hard global exchange contribution computed in QCDF, and also this power spread soft global contribution computed in Samuel's approach. So it will be interesting to combine these two analyses together and see what will happen phenomenologically. We update this B2K LL decays in the end of 2012, and here is the correct results for the bin branch ratio B2K LL. The external results for Bell, CDF, and HCB also collected here. The most precise measurement from HCB with uncertainties of roughly speaking 10%. Again, there is within 2 sigma level, there is an agreement between theory and the experimental prediction. However, again, if you just naively focus on the central values, generally speaking, the theoretical central value is higher than the experiment did, so you may wonder whether we overestimate these form factors of B2K plus M minus. So if this happens, so you may ask whether this is also the case for B2 pi, and in fact, if that really happens, which may help to resolve this VUB pattern. And this second table I showed you as for the integrate isostream symmetry BGK-LL. I just mentioned it before, all of these three extremity groups, Bell, Baba, and HCB, claim that there are large isostream symmetry for large equal regions, albeit with its large uncertainties. Theoretically, we only predict these isostream symmetries 1% or even less. Okay, now let's come to the conclusions. And it is fair to say that we have durable control of the exclusive semileptonic B decays on the theoretic side due to the development in many different directions, including these factorizing theorems, effective field theory, and non-predicative approaches. And up to now, there is no significant deviations from the standard model have been found. In particular, for this FC-NC value case, where we expect that there will be some new physics. Only a few cases actually occur in semileptonic case, as I mentioned here, VUB pattern and this isostream symmetry pattern. So it is certainly very crucial that better understanding of this higher order and power corrections exclusive B case will be important to searching for this new physics. That's all, thank you.
Question, comment? Please.
Okay, I saw that you showed a diagram with the three pattern. You showed the three pattern contribution.
B mesa for BGK-LL.
Yeah. So the additional soft group, the additional harmonic group can attach the horizontal clock line.
So again, the soft group will what about
Can the soft group, additional group, attached to the?
That is the soft group can go anywhere in this QCD diagram. Of this. Okay, here this soft group actually can enter both either this initial B method state or this chaos state. But in the correlation function level, that is described by
This one, yes.
This non-polyphonic dynamics will only be characterized by these three particle images amplitude.
So the group can attach the horizontal clock line.
It attaches where?
The horizontal line.
Here. This down part or where? This is B quark and this is